Hello and welcome. This is Integral Solver with a very nice looking integral today. And the way I'd like to solve this integral is by using these very important facts right here. They will come in handy later on, and you'll see. But the main solution development for this generalized integral right here comes from Feynman's trick, where Feynman's trick is the special case for Leibniz rule for differentiating under the integral sign. Okay, so I'll start the solution development by defining a function in terms of alpha. And if you're unfamiliar with the Feynman's trick, I suggest you go look it up. That'd be very helpful towards you. And I guess I could place my alpha anywhere inside this function, but where would it be helpful? Well, if we tried plugging it in here, right here, if we tried plugging it here, well, it could be helpful, but not as helpful if I were to plug in it inside the sine function. And the reason why I'd say that, it'd be more helpful to plug it into the sine function, is that we can clearly see f of alpha equaling 1 equals I, and if we plug in 0, f of 0, alpha equaling 0, would that be e to the negative x to the n times sine of 0 times x to the n. And if we know anything about the sine function, this right here will collapse to 0 because sine of 0 equals 0. So we have f of alpha equaling 0 equals 0. Okay. That is a very, very nice thing to have in your toolbox for using Feynman's trick. Okay, so the whole point of Feynman's trick is to define a function and then differentiate the function. So f prime of alpha, and hopefully get a easier integral. That's the whole point of Feynman's trick. Sometimes it doesn't work, but sometimes it does, and in this case it will work. Okay. And we see there are no functions of alpha inside the limits. These would be considered constants, so therefore this would be the special case of Leibniz rule. So we can go ahead and bring in the derivative, but instead of being a regular derivative, it would turn into a partial derivative. So, okay, my apologies. This is all crammed over here. Let me fix this real quick. Okay. This would be equal to the integral from 0 to infinity of now a partial derivative with respect to the parameter alpha. Okay, yes. I hope you can see where this is coming from, and if you can't, I would suggest looking up Feynman's trick. Okay. Now, I will not show the steps of the partial derivative, but if you've taken any calculus or multiple variable calculus, you'll know how to do this. It's quite simple. You'll find yourself at this result. It's very, very simple. Okay, so now that we have this more simplified form of an integral, I would say this would be equal to f prime of alpha. Okay. Now, we can use this very important thing about cosine. I couldn't think of another word. My apologies about that. But if we take the real part of e to the ix, it's equal to cosine of x. This can be found using Euler's formula, which I guess is not here, but I won't state it in this video. But if you use Euler's formula and take the real part of it, you would get the cosine function. Okay, so this would imply the real part of the integral from 0 to infinity of e to the negative x to the n, e to the I, alpha x to the n. Sorry, a little stutter there. It's okay though. It's no big deal. Okay, here we are. I hope you see where this can come from, or where this comes from, because if we take the real part of e to the I times some angle, theta in this case, that would be the cosine of the same angle theta. So in this case, our angle theta would be alpha x to the n. There we go. It is here. Okay, this is very nice. All right, so we can go ahead and combine this form. But I would like to factor out it. Negative x to the n. Okay, cool. This is true, okay. But before I just, well, to solve this integral, I would like to define another function. Let's say lowercase gamma of, say, a. Okay, just a parameter. Let this equal to the integral from 0 to infinity of e to the negative a x to the n. Now this integral is actually pretty easy using the gamma function. And if you're unfamiliar with the gamma function, I will show it in a second. This one we can use a very simple u substitution. Let u equal a x to the n. Okay. Rearranging this would imply that x equals u over a to the 1 over n instead of n. This implies x is equal to, we can just write it as a to the negative 1 over n, gamma, not gamma, sorry, u to the 1 over n, and then minus 1 du divided by n. Okay. Now, if we apply this to gamma of a, this implies that gamma of a equals a to the negative 1 over n times the integral from 0 to infinity. And the limits. If we were to take the limit as x goes to infinity, right here, this implies that u would go to infinity. If we take the limit as x goes to 0, this would imply u goes to 0. So in this case, our limits are not changed, they're not bothered. Okay. Now, this is the gamma function I was talking about. This would be gamma of 1 over n. And if we were to just show that this right here, the gamma function is defined to be equal to this integral right here. But if we let x equal 1 over n in this case, that would be our integral we need for gamma of a. Okay. Very nice. Okay, cool. This is true. All right, nice. So, if we let a, equal 1 minus alpha times I, okay, we would, and take the real part, this right here implies that f prime of alpha equals the real part of gamma, little gamma, of a equaling 1 minus alpha I. Okay. This is correct. I hope you can see where this is coming from, because we have our, sorry about that, our little gamma of a equaling to that. And if we were to plug in a equaling 1 minus alpha times I, and then taking the real part, we would get back our original f prime of alpha. This is true. Which is also equivalent if we look at the result for gamma of A. This would be the real part, gamma 1 over n times 1 minus alpha times I to the negative 1 over n. Okay, this is very, very nice. Okay, so this is f prime of alpha. Now, since this is just a real number slash constant, we can just bring it out of the real part, and we can't bring this one out of the real part. We cannot bring that one out of the real part because we still have a I. It's not just a number. We have to take the real part of the complex number. Okay, so f prime of alpha is equal to gamma 1 over n, real part of 1 minus alpha times I to the negative 1 over n. Okay. And right now, I guess we can just recover f of alpha. So if we were to integrate both sides, we could get back f of alpha d alpha. Okay, I hope you can see this, where this is coming from. And this is just a constant term. We can bring it out of the integrand, outside the integral. So this is 1 over n, okay, divided by n, integral, the real part, my apologies, the real part of the integral of 1 minus alpha times I to the negative 1 over n. Okay, alpha, not gamma, it's alpha. I sometimes mix up the Greek letters. It's okay though. This would be alpha. Alright, now for this integral, it's very, very easy. Remember that I is considered a constant. It's just a constant. We can do a substitution. We will let L equal 1 minus alpha times I. This implies DL is equal to negative I d alpha. Okay, this is correct. And if we remember that I is equal to the square root negative 1, this would imply that if we multiply both sides by I, we have I dl equals d alpha. Yeah. Okay. So we can go ahead and put this over here, make it smaller, put it right there. Okay. I hope you can see where this is coming from. Okay. So this integral would be equal to I from the differential element, integral L to the negative 1 over n dl, which right here is a very easy integral. It's just going to be I times L to the negative 1 over n plus 1, negative 1 over n plus 1. It's just simple power rule. I will go ahead and rearrange the power and the denominator. This is equivalent to n minus 1 over n. Right here, this is the same thing as n minus 1 over n. Okay. And we can go ahead and bring this n up to the top, or bring it right here at least, times, okay. Very nice. So, remember L is equal to 1 minus alpha times I. So right here, this would be n I divided by n minus 1 times 1 minus alpha times I to the n minus 1 over n. Okay. So, f of alpha is equal to what exactly? Well, gamma 1 over n divided by n times n divided by n minus 1 times the real part of I times 1 minus alpha times I to the power of n minus 1 over n. Okay. This is true. Very nice. And since this is a indefinite integral, my bad, you have to add a plus c. Plus c. My apologies, I forgot the plus c. Never figure plus c's when you're doing an indefinite integral. Okay. Sorry about that. Okay. So we can, since this was inside of the integral, we're going to have to add a plus c here, okay? Yes. I hope you can see where this is coming from. I made a simple mistake and I corrected it immediately. That is okay. And if we want to find out what the value c is, we have an initial condition. And that initial condition was, if we recall, f of 0 equals 0. Well, if we plug in 0 for alpha, we have f of 0 also equals gamma 1 over n divided by n times n over n minus 1 times the real part of I times 1 minus 0 times I. Well, 0 times I is just 0, so that's just be 1. N minus 1 over n, well, 1 to any real number, is just equal to 1. So times 1, which is just equal to I, plus c. But the real part of I is 0, so this right here is just 0. So it's just going to be times c is equal to 0. Well, if that's equal to 0, that means c also has to equal 0. So this right here implies that c is equal to 0. Okay. So we can just get rid of this right here. C is equal to 0. This is very nice. Very, very nice. Oh, shoot. Don't want to do that. Oh, no. What did I do? I lost it. Oh, no. It's okay. Alright. There we go. Let me just make this smaller real quick. Trying not to take too much time on this, because my goal is to solve an integral, not to make modifications to the size of a problem. Okay, enough joking. We immediately see we can simplify this. We can get rid of the parentheses real quick. But this n will cancel with that n, okay? And multiplying these out, all we have is n minus 1. Okay, cool. Hopefully I missed something. Yes, I did. Oh well, it's okay. It is okay. Just little mistakes. Okay. This is right. Okay. Alright. Let's see. And we can immediately simplify this and say that I is equal to f of alpha equaling 1, which then equals 1 over n minus 1, real part of I times 1 minus I. Yeah. Very nice. Very simplified. Okay. Let me make sure this is true. Okay. C was a number, so we can take out the real part. Okay, this is correct. Okay, this is correct. Just making sure I didn't make any mistakes. Alright. But we can use a very important fact from, here we go. We have the real part of I times x is equal to the imaginary part of x. I believe this is correct. Okay, let me make sure. My bad, I completely got that backwards. Scratch that, I'm so sorry. I don't know why I thought that was true, my bad. No. The real part of x is equal to the imaginary part of ix. Yeah, that seemed wrong. I apologize for that little mistake. I am very sorry about that. No, but the real part of I times x, I was thinking of the wrong one, is equal to negative times the imaginary part of x. Now this should be true. Yes. Yes, yes, this is true. So we clearly see an I right here. And in this case, this would be our x. Okay. I am very sorry about that first mistake. I is equal gamma of 1 over n divided by n minus 1. Now well, hold on. Negative. Don't want to forget about that negative, because real part of I times some x, which is a complex number, is equal to negative times the imaginary part of that complex number. So we can bring out the negative imaginary part of the exact same thing, except without the I. Okay. Very nice. And we can just go ahead and use this negative right here to just change this 1 minus n, I believe. Yes. This is true. Yes. Okay. 1 minus n. And we can use another important fact. The imaginary part of some complex number z is equal to the complex modulus, or I believe I'm saying that right, sign of the argument of z, where the argument of z is equal to the inverse tangent of, well, if z is equal to x plus y times I, then the argument of that complex number would be right here, this. Okay. Try like this. There we go. Okay. Two more important things. The complex modulus of z to the n equals modulus of z to n. And we have the argument of z to the n also equals the n times the argument of the z. Okay. Alright. And, yeah. And since inverse tan of x is odd, this would imply that the argument of the complex conjugate of z is equal to the negative argument of z. Yes, this is true. Right here should be true. Okay. Very nice. I have covered all of the important facts down here, and I would like to start using them. So, to start with this one, this part of the problem, copy and paste. Okay. This right here should equal the modulus of the 1 minus I to the n minus 1 over n. Okay. Times the sign of the argument, or I am so sorry. I can't even spell anymore. It's okay. Argument of what exactly? Well, the same thing. We're going to have 1 minus I to the n minus 1 over n. Okay. Sorry for my handwriting. It's quite terrible. So, if we look at these things right here, these important facts, argument of z to the n is equal to n times the argument. So we can bring this out. Okay, and let's move this over. We're going to have n minus 1 over n. Okay, and same thing for the modulus. We can just bring this outside. We can just say n minus 1 over n. Okay. But the modulus of x plus I times y is equal to the square root of x squared plus y squared. Okay. We can clearly see, in this case, x would have to equal 1, comma y would have to equal negative 1. Okay. So that means the modulus would have to be equal to the square root, square root of 1 squared plus negative 1 squared, which is just equal to 1. Both of these are equal to 1. 1 plus 1 equals 2. I know. It's crazy, isn't it? Square root 2 to the n minus 1 over n. But the square root of 2 equals 2 to the 1 half. Combine the powers, so this would just be equal to 2 to the n minus 1 over 2n. Okay. That's very nice. And the argument, okay, the argument, I'm so sorry, I'm getting ahead of myself, of 1 minus I is just equal to the inverse tangent of negative 1 over 1, which would just be negative 1, which since the inverse tangent is an odd function, this is just equal to negative inverse tangent of 1, and the inverse tangent of 1 equals pi over 4, so therefore this would be negative pi over 4. Okay, cool. This is very, very nice. I will go ahead and shrink this. Very nice. Okay, and I will move this. I'll make it smaller. Okay. So this right here would be equal to sine, and also I should mention, hopefully you would know this, but if you don't, that's okay. Sine of x is a odd function. Okay. So therefore sine of negative x would just be equal to negative sine of that same x. Okay. So this would be sine of what? N power, pi over 4. Well, I guess that'd be negative pi over 4 since, yes, negative pi over 4 times n minus 1 over m. Okay. And we know that sine's an odd function, so we can just bring this out. Okay. So let's go ahead and put this all together. We have the imaginary part of 1 minus alpha I to the n minus 1 is equal to 2 to the n minus 1 over 2n. Well, negative. If we remember, sine's an odd function. You multiply those together, blah, blah, blah. We get the negative outside. Sine of pi times n minus 1. Okay, I'm really sorry about that. Okay. Divided by 4n. So this is the imaginary part of 1. My apologies. 1 minus I. Okay. Very, very nice. Okay. And if we multiply this by gamma of 1 over n divided by 1 minus n, okay, I is equal to gamma of 1 over n divided by n minus 1 times the imaginary part of 1 minus, well, 1 minus I to the n minus 1 over n. We just evaluated this. We just evaluated this right here. This was equal 1, there we go, to 2 to the n minus 1 over 2n. Okay, and then sine of pi times n minus 1 over 4 for n. Okay. There we go. This is the final result. Looks pretty cool. Yeah, this is how I want to leave it. This is a very nice result. I will go ahead and show. Okay, so this right here is equal to the integral from 0 to infinity of e to the negative x to the n sine of x to the n divided by x to the n. A lot of n's. Okay, dx. Okay, there we go. I hope you enjoyed this video. I hope you maybe learned something. Hopefully you learned something from this video. I'm sorry I didn't give a more explanation about the Feynman's trick or how to prove it or where it comes from, but if you want to look it up, feel free to do that, of course. I suggest you do, actually. But yeah, I hope you had a good experience watching this video.